Let's spend some time covering the boot initialization sequence carried out by your Debian Linux system. So we'll log in from the console as user Linux CBT. This will auto-adjust the resolution momentarily. And let's get our notes going and just discuss what our system experiences when it is booted fully. And this is the case, by the way, for virtually all x86 and 64-bit base systems. So we'll call this the boot init sequence. We'll cover from outside of the operating system to inside the operating system, encompassing both the BIOS as well as grub and subsequently init in the Linux kernel. So the features of the boot init sequence is that it bootstraps or loads a running operating system. Again, this isn't specific, so let's just note, not specific to Linux per se. However, it does apply. So it bootstraps your system from the bare hardware to an operating system such as GNU Linux. A number of steps are involved in this process, and the hierarchy resembles the following. Every x86, x64, and for that matter every computer has some sort of BIOS or basic input-output system which is able to initialize and recognize connected hardware. So at the top layer we have the BIOS. The BIOS is basically the basic input-output system. All computers have this in one incarnation or another, called one thing or another. A common BIOS you'll find on x86 systems tends to be the Phoenix BIOS, even within virtualized environments like VMware, for example, which we're using for this particular study. So you've got the basic input-output system, and this system deals with hardware at its basic layer, which deals with items such as availability, accessibility, and a few other issues. So the BIOS is responsible for ensuring that physical components that should be there are there and that they're functional, including, but not limited to, memory, storage, optical storage or removable storage, and CPU processing power, and any of the power-saving features provided by your motherboard. So it is basic software. It's like a mini operating system that governs over the hardware that makes up your computer, your motherboard and connected components. A layer below, the BIOS hands off its management of the system from a certain point to the operating system in stages. The BIOS consults the bootable hard drive's master boot record, or MBR. So once the BIOS has confirmed the initialization of the system, it hands over control to the master boot record of the bootable hard drive, which is 512 bytes on PCs in size. In that 512 byte zone is enough information for phase 1 of booting an operating system. So in this zone is grub phase 1. From this MBR, the next handoff is to grub phase 2, or 1.5, then 2. So the handoff is then grub 1.5 through 2. And what's happening here is, with this interim step of 1.5, grub is making available the file systems that are necessary, or the file system, the root file system that's necessary to boot your operating system. So the 512 byte range contains enough code for grub to be able to load drivers necessary to find your root file system. So root file system reference. And then when you've selected a menu item from the grub menu, or it has defaulted to a menu item, phase 2 occurs, and that's the actual boot. So this is the handoff at this stage to the bootloader within the operating system, which is the init process. So in a nutshell, BIOS, bootable hard drives, MBR, the bootloader, which is grub for Linux-based systems, and then init, which handles the initialization of the system. So grub is multi-phased. It's split across multiple phases, 1.5, 1, as well as 2, or 1, then 1.5, then 2. Then init loads the services. So Linux services for various run levels are loaded. So this is basically the boot init sequence that takes place when your system is brought up. When init is launched, it sets up the run level environment. And the run levels are referenced from a configuration file beneath etc known as init tab. And in init tab there's a pointer called init default, which references the default run level for the system. So this is your hierarchy, and there are a number of run levels that are supported. And they include run levels 0 through 6, with 0 being a halt, and these are at the same level. 1 meaning single, which is why you can indicate either the word single or the number 1. 2, which is the default multi-user. So 2, multi-user, and it is the default. And 3 through 5, which are also multi-user. The 2 being the default on Debian tends to be Debian specific. And 6, which is the initialization of a reboot of the system. So you've got these levels 0 through 6 that are your default run levels. Others can be defined. Now these run scripts that are initiated are located, so let's just note that init, when consulting run levels, consults a number of scripts, including an initialization script that's run in all but one run level number 1, or single user mode. The scripts that are referenced are sourced or are based in etc init.d. This is a repository for system daemons / services. And these daemons / services are segmented into various run levels where they're applicable via start and kill scripts. So let's just note that etc init.d services / daemons are referenced per run level. Now, without piling on too much more information, let's look at this hierarchy from the OS's perspective since we're up and running. So we'll begin by looking at what init does and then backtrack to the BIOS, then grub. So we're up and running. So init, when it starts, it reads init default. Let's take a quick look at init default, Control-Shift-T in this particular instance, navigate to etc. And init tab contains this entry, init default. It's readable by everyone. Let's cat the contents of init tab, and here's the file. So when init starts, after, of course, the kernel and the initial RAM disk have been called by grub to set up access to the root file system, so that means the root file system is made accessible, init begins its process of setting up the environment. So it reads this file. One of the key directives is the init default directive. It includes the run level that will be the default. For Debian, GNU Linux, it's historically been run level 2. The run level can always be identified from a running system by simply executing run level. Now notice it doesn't come up as a non-privileged user. And let's do a which run level so you can see why. And that's because it's in sbin, a directory that's not in a non-privileged user's path. So we are in run level 2, and the prior run level is unknown, meaning we've booted directly into run level number 2. So one of the key directives is this ID for the init default ID followed by the number. Additionally, notice that there is a reference to etc init.d RCS. This is a script, a system configuration initialization script that is always executed regardless of run level with the exception of when booting into emergency mode. So the items referenced in this script are always called. And for each of these items, if we navigate into init-d, for example, we'll see their references. These are the scripts, by the way. Here's RCS. RCS is only 117 bytes, so let's cat its contents. And as we can see, it initiates the shell, and then it simply references that it will execute RC and start. So RC start is the default run level that's called regardless of the various run level that's in play at any particular time. So that's RC, that's the run control script. S, that's called. So it sources some functions that sets up the environment for us to be able to use. Now we're in the directory that contains the various services and daemons that govern this system. Here they are sorted from A to Z. Some may look familiar, for example, the SSH service that is made available for us to connect across the wire to this system, or perhaps even NFS, or as we can see here, our syslog, which handles logging, or cups for printing, or cron for job scheduling. So this is where you can find the scripts. Now, by the way, if we do a file against star, you'll see that these scripts are largely shell scripts. They're painted or colored green to indicate that they're executable. In a colorized shell within a GNOME desktop environment, executable files are colorized green so that you can visually indicate that they're executable, as opposed to non-executable items, which in this case tend to be colored black or other colors to symbolize other things such as broken symbolic links and otherwise. So these items are all executable and can be run directly from this directory or reference using the absolute path. So that means you can start and stop services, check their statuses and so on directly using this directory in the name of a script, for example. So this is the container or repository for all of the scripts that are run when the system comes up. But again, as we've mentioned, these scripts are called in various orders to be started or initiated or terminated appropriately based on the run level that's in play. When we lsrc using tab completion, we see that the run levels that correspond to the various init supported run levels 0 through 6. So in the directory 0.d are all of the scripts that apply to run level 0. Well, what happens when run level 0 is called? As mentioned, the system is halted. So that means the directory should contain kill scripts. Let's take a quick look at rc0.d and notice the references for kill. Now, any script that is to be terminated will be referenced via a symbolic link with a prefix of k and a number or a numeric identifier following the k to indicate the order in which the process is to be killed. So here are various kill scripts for various programs. For example, here is a kill script for the exim4 MTA, which is a symbolic link to initd exim4. So let's see what this all means. So etc, and this is rc0.d, so rc0.d contains items such as the following. This is a kill script for the exim4 service / daemon. And it specifies that it's a kill script with a leading K, uppercase, followed by the numerical identifier indicating the order in which the item is to be killed. So a script that contains a prefix of K followed by 01 will be killed before a script that contains, let's say, 02, as in avhi daemon, or 03, and so on. And of course, where the numbers are identical, then they're processed in alphabetical order. So exim4 will be killed before fuse, fuse will be killed before gdm3, and so on. So in run level 0, we expect to find kill scripts. In fact, we don't expect to find start scripts. Let's take a quick look at the single user mode. So this is 1.d for single user mode. Notice, again, a number of kill scripts to ensure that networking services are not running, such as port map, NFS, rsyslog, and so on. But there are a couple of items that are important, such as killing processes, logging the boot up, and executing a single mode environment. So rc1.d contains some start scripts, for example. Let's take this item and just reference it as an example. So as you can see, this is how the init process organizes. This is a system V or system 5 organization of run control scripts. So this item here, this is a start script for single user mode, referenced in rc1.d. So any combination of kill and start scripts will be processed by init accordingly. Now again, notice that they're just symbolic links to one level up into init.d to the name of the script. So that means the script is really in existence once and cross-reference as necessary. And as we can imagine, in rc2.d, we expect to find a lot of start scripts. Here are your start scripts to set up the second run level, which includes GDM3, which is the GNOME Desktop Manager version 3, as well as a number of other items that are important, such as, for example, Apache 2, which we set up when we initiated the configuration of the system, and SSH. So SSH, in the order of things, starts after Apache in run level 2, for example. So that's how init references the various scripts that are of interest for a given run level. Now you can use init to enter a run level at any time by just referencing init from the command line as root followed by the desired run level. So for example, note you may use init as root to enter /exit run levels at any time. So if we're currently in run level 2 and we'd like to enter single user mode, we just simply execute. So for example, init1 enters run level 1, or init6 reboots the system, or init0 halts the system. So when you execute reboots, you're really calling it init6, or a halt, such as system shutdown, you're really referencing an init0, which is why it's good to know that you can reference these commands directly from the shell. So again, just a quick recap. You turn on your machine, the BIOS takes over. It checks that hardware is present. It finds the bootable hard drives, master boot record, and loads the code there, grub phase 1. Grub then takes over 1.5 and provides file system support using drivers that are loaded from a different portion of the hard drive. Then when you've selected an option, you're in grub phase 2, it starts, it loads the kernel, the initial RAM disk, which loads support for the operating system, and then control is passed to init, which is process ID number 1 on all Linux and Unix systems, which then initiates RCS to set up the environment, followed by all of the start and kill scripts that apply to a given run level. And that's defined, as mentioned, in init tab. So init tab spells out that a default script is called. It also spells out what the various TTYs are that are defined, meaning shells that are accessible on different TTYs. So for example, here we see get TTYs on TTYs 1 through 6, which allows us Control-Alt F1 through F6 access to those shells. So at any time on a Linux system, there are other shells available that you may use by using or cycling through Control-Alt F1 through F6, with normally the GDM or KDM or the graphical environment on Control-Alt F7. And the init tab also includes some examples of how you may place get TTY on serial ports for console access, which can prove to be quite important in lights out situations. So for example, you could put get TTYs on comms 1 and 2, and then via consoles, via terminal boxes in the data center, connect to your Linux box and execute whatever management procedures that are necessary. Now normally we have SSH or telnet access, preferably SSH, but oftentimes it's important to have at least basic console access in the event that the operating system becomes unavailable. akin to console management, for example, of a router or an infrastructure device like a switch or firewall. So that's the init portion of things. So how do we back up and take a look from the beginning of how all of this works? Again, this is not specific to Linux. The only specific portions would be from grub on. But then again, grub can be used to boot other operating systems like Windows. So really, every operating system has some sort of bootloader, which then calls whatever drivers are necessary to set up that operating system. So for most, if not all computers, BIOS, then bootable, then bootloader is the standard modus operandi. So with that said, what we should do is close this, reboot the box, and just take a brief look at the other components that are involved. Let's SU in and execute an init. In this case, we're not halting, we're rebooting, so we can take a look at the startup process. Now this will kill, by the way, just as a quick reminder, when you enter run level 6, for example, what's essentially happening is as follows. These kill scripts are executed in the order in which you see them. So these programs or services are killed, and after fuse, GDM is killed, which is why when you initially execute an init 6 or switch run levels causing certain services to be killed, for example, it takes a blip or so, or an instant, before you lose GUI access, and that's because the GUI isn't killed first. It's labeled 1, but alphabetically it comes after Bluetooth, @daemon, Apache 2, Anacron, and so on. And similarly for SSH, if you enter run level 6, then SSH will be killed wherever it is referenced in the list. So let's go ahead and init 6. And by the way, it could also be referenced from some sort of common caller as well. It doesn't always have to be referenced explicitly. So let's go ahead and init 6 and take a look at the other portions of this process. And just like that, we're back. This is a fast system, so it comes up rather quickly, not giving us much opportunity. But in a nutshell, if you notice, we saw the quick flash from VMware and then the handover to the bootable hard disk. So there wasn't much time to interact. But the BIOS quickly found its default 10 gig hard drive, searched the MBR, and it found grub phase 1. Now, when we select one of these particular options or leave the operating system to default, phases 1.5 and 2 are enacted. The initial RAM disk and kernel are called to set up the environment. And then after that, init takes over. Once init takes over, it goes through the procedure that we've mentioned, which includes running the default run control script, RCSD, or RCS that is, and followed by the appropriate kill and start scripts for the run level in which to enter. Now the run level is influenced by the options that are passed on the command line or via init tab. So if you edit an option like this option, for example, the line that contains vmlinux, which is the reference to the kernel, supports any number of parameters that drive how the kernel is instantiated. And this is true across distributions. So at the end of this line, if we indicated 1, for example, it causes the instance to, or the startup, to drive the operating system into run level number 1 as opposed to the default of run level number 2. So when init starts, it reads init tab, but if an option is specified on the command line, then it overrides init tab. That's in essence what happens. So specifying 1 or single overrides init tab, or any parameter passed to the kernel on the command line overrides etc init tab's init default setting, which is that all-important setting, because this gives you entire control over the process to help you debug in the event of trouble. So let's try to boot this option. Again, when you make changes, if you press escape, it discards the changes. So you really need to make the change and then Control X to boot, at least with this version of grub, as opposed to prior versions, you would simply B to boot. So 1, and this will enter single user mode momentarily. This will set up the appropriate processes for run level 1 mode. Again, there are some basics that must take place even for run level number 1, such as setting up the file system and so on. Now, if we elect to not specify a password at this point in the boot process, as we've mentioned earlier, then init continues to read the default boot up run level from init tab in etc. If we specify a password, then it propels us into single user mode. When we execute run level, it tells us that it's single user mode or run level number 1. And at this point, we have full root access to the system. In single user mode, only root has access to the system, which begs the question, can you SU as a user such as Linux CBT? Certainly can, but you authenticate only as the user root. You're not presented with the ability to authenticate as a non-privileged user when connecting in single user mode, because the idea is that single user mode is reserved for administration. And notice a password is required in order to enter single user mode. Otherwise, Debian boots into its default incarnation. So let's see. If we navigate into etc and take a look at init tab, the default incarnation, as mentioned, is indicated on that line which references the default run level ID to init default, with references to RCS, what to do with SU login, and a few other items, such as where to put TTYs and the directories where to launch the various run levels from, and so on. So we have full access to the system. Now, to enter a different run level, such as the default, we could just execute init2, which is the default. This will then load all of the services. So in essence, it basically causes init to navigate into rc2.d and execute all of the start scripts that are found here. And if any kill, it'll execute them, but none exist, just start scripts, and it'll execute them in the order in which they're presented. In the case of GDM, we can see it's 21st on the list, so if we grep GDM, then it's loaded in the 21st order. And eventually, towards the end of the process, we have a graphical environment. Now, insofar as the processes that are running, the command that's used to enumerate the running processes is ps. So if we ps ef or aux, either or, we'll enumerate the currently running processes for all users on the system. Now, the output in this resolution is hard to deal with, so we'll pipe it to less. It's not paginated without a paginator such as less or more. So towards the top, we see some columns, UID, PID, PPID, so on and so forth. The PPID is the parent process for a given process. So notice that init has a PID or process ID of 1, and its PPID is 0, which is the scheduler, the system scheduler. So the kernel actually loaded init as the first process, PID 1. And then other processes reference PID 1 accordingly. So init is the first process ID launched by the scheduler. And then you'll see references to other programs. Now we're in single user mode, so there aren't as many references, or any for that matter, defined just yet. But once the system resumes, you'll see those references. So to enter a different run level when in single user mode, there are two ways. You could init6 to reboot. You could also outright type reboot, which is in sbin, or just enter the run level that's of interest directly. The init process is smart enough to load only those services that are necessary. So let's enter the default run level of number 2. And as we saw, init loaded the services in the order in which we expected it to. As mentioned, as part of this whole boot init sequence, a number of get TTYs are spawned on all Linux systems, unless they've been suppressed by an administrator. They're accessible via Control-Alt F1 through F6 normally. So Control-Alt F1, for example, places us on console number 1. And notice it reads TTY1. If we log in on this console, it's independent of other consoles, as root for example. We can execute the command TTY. TTY is in user bin. It's available to everyone. It identifies the TTY to which your current session is connected, whether using SSH, Telnet, or logged in at the console, or via a GNOME or KDE or graphical virtual terminal. So this TTY tells us that we're on TTY1. if we grep tty1 from etc init tab, for example, you'll see that a get tty is spawned at 38,400 bits per second on tty1. So this is indeed the console to which we're connected. It has a respawn option, which means if it crashes, respawn it. And this tty is made available in run levels 2 through 5 or multi-user run levels. Notice no pointer to single user run level. So that's tty number 1. Control Alt F2. This is an independent tty for which we may log in as a different user, for example, the user Linux CBT. We're logged in as a non-privileged user, but we may also execute tty to show that we're connected to dev tty2. And by the way, to determine the number of users connected to your system at any time, there's a host of commands, W commands, that are quite helpful. W, for example, shows the users that are connected to your system. So notice that on tty number 1 is the user root. And that user logged in at 1328 compared to the current time, 1330, so 2 minutes ago roughly. And the user is running a bash shell. At the time that the user in this shell executed W, it reflects that the user executed W, and the user logged in a minute later roughly at 1329 on tty2. Now let's go to tty3, for example, log in as Linux CBT here again, and execute tty, and then W. Now W shows 3 connected users. On tty 1 is root, 3, the new user, 1330, 2, the former incarnation. And there's still other tty's available, such as 4, 5, 6, and back to 1. Now we can kill all these sessions by simply logging out. It's a good suggestion to reset the buffer and then exit, so that there's little evidence as to what's on the screen. There are other ways to handle this. You could have a logout process that clears the screen if you'd like. Let's log out each session. Notice the default clearing in that case. And now these are all clean. Now to return to the GUI, Control Alt F7. Sometimes you'll find your GUI on Control Alt F8 or some other function number. So just take a look, cycle through, toggle through to see what's available. So that's the process of booting your system. BIOS, bootloader, then init, after of course the init.rd and the kernel, which perhaps we should just intersperse since we tend to, but it's quite quickly overlooked because it happens so quickly behind the scenes. Let's get our notes going. By the way, I'm referencing !gedit in this case. This simply means, from a shell perspective, to execute the most recent invocation from the history of gedit. So for example, if we history, we see a number of commands. If we history and then pipe the output into grep and search for gedit, for example, we see a number of gedit commands. I want the most recent instance, which is 22. So that will bring up that particular instance, which brings up our notes. We could have also executed !22. So for example, we know that gedit was last executed before at 22, now 54. So !54 brings up that instance equally the same. So the boot process, BIOS, and then we've mentioned grub is found, and we should just intersperse between grub and init, because this phase 2 portion, 1.5 to 2, is really a call to init.rd / Linux kernel, and then on to mounting the file system, and then the call to init. But it happens behind the scenes, so sometimes it's not even worth mentioning. So that's a process of booting your system regardless of the operating system you are involved in executing.